Let us now see when we say a function is differentiable at a point C and what its derivative is. We say a function f from I to R, where I is an interval, is differentiable at a point C in I if limit x tends to C f of x minus f of c divided by x minus c exists. Moreover, if f is differentiable at C, we say that f dash of C, that is the derivative of C, is equal to limit x tends to C f of x minus f of c divided by x minus c. Notice that here f dash of c is a notation for derivative of f at c. And this derivative measures how the output changes for a small change in the input. By taking the limit, we are ensuring that we are not looking at any particular amount of change, but we are looking at arbitrarily small change in input and looking at how much the output changes accordingly. More on this can be found in the previous video on the intuition for the definition of derivatives. Equipped with the definition of differentiability and derivative, now let us look at some examples. Okay, first example. Let us look at the function f of x given by x. Is this function differentiable at a point C? It is. How do you check this? What we are interested in is if we want to see if limit x tends to C of f of x minus f of c divided by x minus c exists or not. That's what we have to check. But what is f of x? F of x is equal to x. And what is f of c? F of c is equal to c. So you want to check if limit x tends to c, x minus c by x minus c exists or not. That's what we have to see. But x minus c by x minus c is nothing but the constant 1. So all we have to see is if limit x tends to c, 1 exists or not. And which we know it exists and is equal to 1. So the derivative of the function f of x equal to x exists and is equal to 1 at all points. Now let us look at a slightly more complicated example, which is f of x is equal to x squared. How do we see whether this function is differentiable at a point or not? Okay, so we have to check limit x tends to c of f of x minus f of c by x minus c. If this exists or not is what we have to see. But this is nothing but limit x tends to c of x squared minus c squared, because f of x is equal to x squared, divided by x minus c. Okay, which is equal to limit x tends to c of x plus c. Correct? Because x squared minus c squared is equal to x plus c into x minus c. So we can cut the two x minus c's. So what you get is x plus c. And this is nothing but 2c. So the derivative at c depends on c. It is equal to 2 times c. But it is differentiable. At every point c, this function is differentiable. Now that we have seen some examples of functions that are differentiable, let us see one example of a function that is not differentiable. The third example is, look at the function f of x is equal to mod x. Okay. So again, we have to look at limit x tends to c f of x minus f of c divided by x minus c, which is equal to limit x tends to c mod x minus mod c divided by x minus c. Now in this case we have to look at three cases. What is case 1? Case 1 is c is greater than 0. If c is greater than 0, then there exists a delta naught, okay, which is actually equal to c by 2, such that if x belongs to c minus delta naught to c plus delta naught, then x is also greater than 0. So you choose this neighborhood of c, and in that neighborhood what happens? Mod x is equal to x as x is positive, and mod c is also equal to c. So because of this, limit x tends to c of mod x minus mod c divided by x minus c is equal to limit x tends to c of x minus c by x minus c, which is equal to 1. Okay. Similarly, if you look at case 2, which is given by c is less than 0, then similarly there exists a delta naught such that if x belongs to c minus delta naught to c plus delta naught, then x is less than 0. And because of this, limit x tends to c mod x minus mod c by x minus c is equal to limit x tends to c of minus x, because here now mod x, because x is negative, mod x is equal to minus x, minus c divided by x minus c. And this limit you can find is equal to minus 1. So if c is less than 0, the limit is the limit exists and the derivative is minus 1. If c is positive, then the derivative exists and the derivative is equal to plus 1. But what happens if c is equal to 0? That's the next question. Finally, we see the last case, which is equal to case 3, that is c is equal to 0. If c is equal to 0, what happens? If c equal to 0, what we are interested in is limit x tends to 0, f of x minus f of 0 divided by x minus 0, which is equal to mod limit x tends to 0 of mod x by x. Okay, now there are two possibilities. X can be positive or x can be negative. Suppose we look at, so for example, you look at two sequences, let's say 1 by n that converges to 0 and minus 1 by n that converges to 0. Okay, let's call these two sequences xn and yn. Both xn and yn converge to 0. But on the other hand, if you look at mod of xn by xn, that is equal to 1 by n divided by 1 by n, which is equal to 1, okay, which converges to 1. Okay, so limit n tends to infinity of mod xn by xn is equal to limit n tends to infinity of 1 by n by 1 by n, which is equal to limit n tends to infinity of 1, which is equal to 1. On the other hand, if you look at limit n tends to infinity of mod yn by yn, that is equal to limit n tends to infinity of 1 by n divided by minus 1 by n, which is equal to limit n tends to infinity of minus 1, which is equal to minus 1. Okay, so we get two different limits, 1 and minus 1. So from the sequential criterion, we can see that the function mod x by x does not have a limit at x is equal to 0. We can also pictorially understand this phenomenon. So if you look at the graph of mod x, it looks something like this. Okay. So in sum, what is happening is at 0, we are having a corner. Okay. So in some sense, if you have a corner, then you fail to be differentiable. Of course, there are other ways to fail from being differentiable, but this is one of the way in which a function can fail to be differentiable. And that's exactly what is happening for this function. And for this reason, this function is not differentiable at 0.